Okay, so hello everyone connecting to this webinar. If you wanted, you can just put on your microphone and say hi.
Hello.
Hello, you,
Hello,
Joachim.
everybody.
Hi.
Hello.
Hello. Hello.
And you can put on your camera also if you want to. You see us, the host team up here.
Good morning.
Hello,
Good
Imre.
morning, everyone.
Morning.
Morning.
Good morning, everybody.
Good morning.
Good morning.
We are really looking forward to this. We've just been fighting a bit with the video we will show. So we think we got it all set the last minute.
All right, so welcome everyone. I think it's 10, Madeleine, we can start if you
Yes.
share the presentation. While you're doing that, I would like to welcome everyone. It's a pleasure to have you with us today, this morning, where my colleagues, Josef and Judith, will talk about introduction to molding materials for metal casting. It's actually the second webinar in the module of ferrous alloys in a series of webinars that we do in the WebLearn project. I will introduce the WebLearn project soon. And here you see the list of participants in the in this webinar. It's a great pleasure to see all of you from 24 participants so far from all around the world, as you can see, from more than 7 countries. It's a very international set of participants and makes it even more interesting. So it's our honor to have you with us. Next slide. As I said, this webinar is one of the webinars in the series of webinars that we have in WebLearn project. It's a project that is financially supported by Knowledge Foundation in Sweden, KK Stiftelsen in Swedish, as well as Jönköping University. And the focus of these webinars is component manufacturing in metal and polymer industry. So we cover different technical aspects, process optimization, for example, sustainability matters, simulation optimization, and so on, related to component manufacturing for metallic and polymer components. It's a project that will continue until at least autumn 2022, within which we will have around 30 to 40 webinars in the topics related just mentioned. There are a lot more information in our website. I invite you all to look at our website, ju.se/weblearn, and read more about the project, as well as the upcoming webinars that are coming through the project. Every 2 weeks, we have a webinar in different topics. Next slide. You see the moderators for this webinar. The one on the left is myself talking about right now. And on the right side, you see my colleague Madeleine Zetterlind at Jönköping University School of Engineering. And it's our pleasure to be your host today. Next slide. But most importantly, or more importantly, you see the presenters for this webinar, or the lecturers. My colleague Judith Svidro, who is a research fellow, a researcher at Jönköping University with specialty in the field of molding materials, especially molding aggregates used in foundry technology, as well as my other colleague, Dr. Josef Svidro, who is a senior researcher working in the area of metal casting with a special focus on molding and core making methods and phenomena at the metal mold interface. You will also watch a video that has been recorded by our other colleague, Sten Bergman, who is right now a retired process engineer who used to work in Volvo Group trucks operation, and you see more practical information related to the topic. Next slide. Here you see the agenda for very summary of the agenda for today. Until 11, we will have presentations from the lecturers or presenters that I introduced. And after that, we plan to have a discussion forum within you, the participants, in order to make sure that there's more discussion on the practical matters related to the topic, as well as the opportunity to do a bit of networking for you. And hopefully by 11:30, we wrap up the discussion and the whole webinar. Next slide. How do we run the webinar? I would like to invite all of you to mute your microphone during the webinar. You are more than welcome to raise questions in the chat during the presentation. And at the end of both presentations, we will raise the questions to the presenters, and there's opportunity to answer to some of them. If there are too many questions, of course, we will take some of them after the webinar. As I mentioned, we try to make our webinars a little bit different from conventional webinars, and in that we try to put a group discussion at the end of our webinars. It's a very important part of our webinars to make sure that there's an opportunity for you to give inputs and share ideas between yourself and also with us. So I hope all of you will stay until the end of the webinar, and we would love to hear your voice as well. Our webinars are recorded and they will be available to you afterwards, those who registered to the webinar. If you don't like to be seen in the recorded videos, please turn off your camera. We will only record and share the presentation part. We will not share the part that is related to group discussion. So when you go to group discussions in breakout rooms, you're welcome to turn on your camera, because those parts will not be shared. Next slide. And in case you have not used Zoom so much, I would like to mention that on the bottom of Zoom window, on the left side, you can see mute and unmute for microphone, as well as turning off and on for the video. And in the middle, you can find the button for chat function, where you can raise your questions to us. Next. That was the introduction from my side. Now I would like to welcome my colleague Judith Svidro to start the presentation about introduction to molding materials.
Thank you, Hassan. So let's start with the basics. When we are talking about molding materials, is the basic aggregate. Next. Okay, but first of all, what is molding material? It's a mixture of different types of aggregates, bonding agents, and additives, which is suitable for the production of molds and cores for sand casting. Foundry aggregate is the main component of these mixtures. The amount of it is dependent on the type of the mixture, but it's usually between 94 to 98% in organic and inorganic systems, and 84 to 90% in green sand based on the weight of the mixture. Since the majority of the mixture is aggregate, it is essential to know the aggregate we use. Next. Yeah, next slide, please.
Sorry, it's
slow.
It was the same last time. Now.
Yeah, now I'm back. Yes, thank you.
Sorry for that.
No problem. So the term sand in its simplest definition is a granular material ranging in the size of 0.05 to 2 millimeters in diameter. Based on the origin, there are naturally occurring sands, And here you can see the most commonly used natural mineral sands. They are chromite, olivine, zircon, and of course, silica sand. These are found in earth crust and are weathering products of crushed rocks. These are the most frequently used molding aggregates. Next slide. The other group of foundry sands are the artificially made ones, manufactured by, for example, physical-chemical processes. So this is why I personally prefer to use the term aggregate when it comes to a general or broad appellation of these materials. Next. Aggregates used for core and mold making need to meet some general requirements. For example, they need to have suitable granulometric properties, so suitable particle size distribution and grain shape. And their chemical composition and pH need to be consistent. They must have good dimensional and thermal stability at elevated temperatures. And of course, they must be compatible with the applied binder system and so on. There are now many types of aggregates that are suitable for core and mold making, but each has distinct advantages and disadvantages. Since changing the molding media to solve a foundry problem is difficult and expensive, the selection is important in the planning phase, but knowledge is the most valuable. To know the material we use, to understand how they behave and why do they behave like that. Next. So let's see silica sand, the most commonly used aggregate for molds and cores. Silica is the term applied to silicon dioxide. Its mineral name is quartz, and quartz is the most common mineral on Earth, so it's abundant and easily mined. It's the weathering product of granite, and it gets its rounded shape after further breakdown and deposition. It always contains some side constituents. I would avoid the word impurities because they are naturally present in silica sand, but they affect, for instance, the thermal stability of the sand for sure. So silica is suitable for all types of molding mixtures and is easy to reclaim. But then why isn't it the perfect foundry sand? Well, because it has some disadvantages as well. The melting point of quartz is above 1700 degrees Celsius. And up to this temperature, it undergoes a series of crystallographic phase transitions. Next. The first and most important in foundry practice is at 573 degrees, when alpha quartz transforms to beta quartz. The changes in the crystallographic structure lead to changes in the density, so expansion of the grains occur. The transformation takes place at a sharply defined temperature, but it is preceded over a range of temperature from like 200 degrees by a progressive change in the physical properties of alpha quartz. From the metal mold interface, the layers of the mold heat up to a range of temperatures due to the relatively low thermal conductivity of the mold. Therefore, the rate of expansion is also different based on the distance from the casting surface. This can lead to mold deformation and spalling and can cause casting defects such as veining. Of course, nowadays, special additives exist to avoid these kind of defects, but still it's important to understand how they work. They can either cushion the sand and give space for its expansion, or promote the next inversion that is also accompanied by expansion. This secondary peak of expansion levels off the volume difference in the layers of the mold, avoiding the cracking and building up tensions. At higher temperatures, the transitions are irreversible. It means that they take place only as quartz is heated. During cooling, different allotropes form, but these temperatures are not reached in the mold or only in a very thin layer next to the metal mold interface. Next. Olivine, named after its olive green color, is a solid solution of forsterite and fayalite. Olivine is a naturally occurring mineral processed by milling. Therefore, the shapes of the particles are those of crushed rock, so angular. And angular shape means higher binder demand and poor sand compaction. It's not easily sourced, and its quality can vary depending on its location. It often contains serpentine, and in this case, the sand must be calcined to eliminate the water. Due to its high acid demand, it's not suitable for acid cure systems, but it's suitable, for instance, for green sand applications. But some advantages as well. The specific heat of olivine is close to silica, but its thermal expansion is far less. And also it's chemically less reactive. Next. Chromite is a naturally occurring spinel consisting primarily of the oxides of chrome and iron. It may contain hydrous impurities like serpentine that can contribute to like pinholes and gas defects in castings. It's very, very important to avoid the mixing chromite with silica sand because a low melting point slag can form that is capable to soften the surface of the chromite sand. Thus, the risk of burn-on defects and penetration increases, which basically chromite sand has very good resistance against. Chromite also has high refractoriness and low expansion. And due to its high density, it has a good chilling power. So it's excellent when a rapid solidification rate is required, particularly for steel castings. And it's also cheaper compared to zircon. Next. Zircon is a zirconium silicate derived from igneous rocks. It consists of very fine grains, and it is seen in this image as well. These images have the same magnifications, these and the ones that were previously shown. So it's obvious that it has finer grains compared to the other sands. Zircon has low thermal expansion, but also high costs. It's particularly used when for instance, investment casting as coarse refractory, and for specific core processes producing thin-walled internal cores mixed with silica to decrease the thermal expansion and avoid cracking. And also when cores are subjected to high thermal stress. It has high density, so zircon also has great chilling power. On the other hand, this high density leads to significantly greater mechanical handling challenges in the foundry because it's found to be abrasive towards tooling. Next. There has been a long-standing interest in using minerals for molding different from the typical foundry sands in the effort to avoid casting defects which arise from expansion and reaction between metal and mold material, or to get smooth casting surface finish and so on. Usually they are manufactured by physical chemical processes. They are products of sintering and melting processes produced in a granular form or turned into granular form by grinding, for instance. They can be aluminosilicates, technical ceramics, sintered ceramics, and so on. Suppliers constantly come up with new products that are claimed to be suitable for specific purposes. For instance, hollow ceramic spheres, which, just imagine, have extremely low thermal diffusivity and can be used even as insulating material. Low thermal expansion, high refractoriness, high sphericity. The palette is broad. One thing is common: their properties are well controlled. So they are used for core making and mold making because they are characterized by better physical chemical properties. Next. As I mentioned, these aggregates are suitable for core and mold making only if they comply with some requirements. And to check it, quality control methods exist. If we think about the cycle of the molding material in a foundry, we see that the first part is the arrival of raw materials, so the new aggregate materials. Of course, all suppliers provide certifications of their materials, but quality control measurements may take place at this stage to monitor the main properties. It's also important to check the quality of recycled aggregates as their performance. Acid demand value shows the catalyst demand of the sand when it comes to acid-cured self-setting mixtures. Grain shape, grain size distribution, and specific surface area together are called granulometric properties, of which grain size distribution is the most foundries. Next slide. This attribute is measured by sieve analysis, and from the results further parameters can be calculated, which are used to quantitatively characterize the aggregates, like average grain size and grain fineness number of the American Foundry Society. Next. Foundry sands generally consist of 3 main fractions and smaller amount of additional fractions. This is optimal from multiple points of view, like compaction and permeability properties. Grain size distribution has significant role since so it's controlled also during the life cycle of the aggregates in the foundry, both when the aggregate is reclaimed or recycled. Next one, please. Yes. So it's a way of controlling the amount of coarse fractions, like agglomerates and also fines, because the growth of both fractions has detrimental effect on the properties of molds and cores, from shifting binder demand and decreased strength to decreased gas permeability. So the results of sieve analysis may indicate actions in the molding line. Next slide, please. The shape of grains has importance from many aspects. However, investigation of the shape and its influence on certain properties is more the topic of research studies than a quality control tool. Characterization techniques has improved a lot lately. And instead of visual examination of the grains and such images presented before, and comparing them with this chart on the left. This is called static image analysis. New technique exists, so-called dynamic image analysis, when the grains are falling through freely in front of a camera that detects two indicity are calculated tells where the surface of the grain is of the sphere. Since the grain size distribution can be calculated as well this way, so it can be useful for foundries with sand lab as well. Next slide, please. So these were the very basics of molding aggregates, and there are many more properties and phenomena that can be and are studied about the behavior of aggregates, their thermophysical properties, the importance of their composition, and how the recycling affects their properties. And I hope that next time you will join as well and we can learn more about these interesting materials. Next. So for today, I would like to thank you for your attention. And with that, I give the word to József. Thank you.
Yes, so after talking about basic aggregates in molding materials, now we will go further and discuss what kind of mixtures and molding and core-making systems can we have in cast iron production. Next, please. So a little bit of history as introduction. One of the earliest handbook type description of molding materials came from an Italian foundryman named Biriguccio in the 15th century. He was the first man to set down from foundry practice in great details with a clarity of analysis and with common sense. His book Pyrotechnia came out posthumously 1540. And in this book, he is highlighting the importance of molding materials by emphasizing the knowledge of making the molds well as one of the principal actions necessary to produce castings successfully. And he also described the preparation method of loam, which is an early molding material, which were used for bronze and brass castings, for example, for bells, as you can see in this picture. Next, please. So we have now listened to Judith. We know what kind of aggregates we have. And after we have these aggregates, we can mix them with different binders, resins, or additives. And then we have a ready-made molding material, which we can use based on our specific application. Next. There are two major groups of casting methods based on the types of molds and cores. By using a permanent mold, we can use a ready-made mold more than one time. In this case, molds are made of mainly metals, thus the application of patterns are not always necessary. This group includes gravity die casting, centrifugal casting, and continuous casting. If we have a non-permanent mold, we can use it only for one occasion, since it got destroyed through the casting process. On the other hand, to make non-permanent molds, we can use a non-permanent pattern, for example, in investment casting. Making non-permanent molds with permanent patterns is called sand casting or sand molding, which is primarily used in cast iron production. In this group, we can distinguish hand molding, automated molding, shell molding, core blowing, and vacuum molding, and now lately 3D printing. Next, please. So let's see what types of molding systems are we use in general in cast iron production. There is a wide variety of binder systems suitable for production of molds and cores. We can distinguish two groups based on the type of bonding. We have physically and chemically bonded mixtures. Green sand and vacuum molding are physically bonded systems. Chemically bonded group has two main subgroups using organic resins or inorganic binders. Inorganic systems can be self-setting and gas-cured or dried, while organic systems can be also self-setting, gas-cured, or even thermosetting. There are overlappings between the groups. Some tricky mixtures need both gas curing and sometimes elevated temperature regarding to the production method, for example, the epoxy sulfur dioxide process. In cast iron production, the widely used mixtures are green sand, self-setting furan sand, the phenolic urethane cold box or the simply cold box process, and gas-cured water glass. We are now going to discuss these mixtures in details. Next, please. Green sand is one of the oldest solutions to bond sand particles together for foundry purposes. Its main advantage is the fast production rate. Bonding takes place due to physical reaction, the expansion of particular mineral at room temperature. The most important component for green sand mixture is bentonite, which is a white-colored granular material with a grain size smaller than 2 microns. The main ingredient in the bentonite is a mineral called montmorillonite with a structure of 2 tetrahedral sheets of silica sandwiching one central octahedral aluminum sheet. As these layers can bond water due to water absorption, this bentonite will expand, and then the physical bonding will be ensured for the whole mixture. Next, please. Green sand is used only for mold making. Its commonly used parameters in case of ferrous applications is 6 to 8% bentonite based on the weight of the sand and 2 to 4% of water. The most important issue regarding to bentonite is activation. Based on the type of ion, we can distinguish calcium and magnesium bentonites, which are naturally available, but their expansion properties are quite low. On the other hand, sodium bentonite is very rare, at least in Europe, but is more suitable for molding purposes due to its high expansion. For this purpose, naturally common bentonites can be converted to sodium bentonite by the exchange of calcium and magnesium ions with the addition of sodium carbonate. This figure shows the difference in strength between sodium and calcium bentonites, so activated and unactivated bentonites, in the range of optimal water content. Next, please. If we go further to chemically bonded systems, one of the most prevalent molding mixture is furan sand, which is a self-setting cold process. That means the bonding will take place through chemical reactions at room temperature. The main components in furan sand are furfuryl alcohol or furfuryl alcohol-based resin, which is produced by condensation reactions of furfuryl alcohol and addition of carbamide and formaldehyde. In furan sand, we also have a hardener, which acts as a catalyst. And these are, in most cases, water solutions of acids, polytoluene sulfonic acid or phosphoric acid. Furan sand is used for both mold and core making. And its commonly used parameters in ferrous applications are 0.8 to 1.5% resin based on the weight of the sand, and around 30 or 40% addition of acid hardener based on the weight of the binder. Next, please. The curing mechanism in furan sand is quite simple. So once we have the phenolic resin or the furan resin and the catalyst mixed to the sand, a polymerization reaction will take place with the byproduct of water and then we will have our ready-made cured mixture. Next, please. Most important furan resin property is the furfural alcohol content. The higher the furfural alcohol content in the furan resin, the higher will be the grade of the resin and also the price. And nitrogen content and water content are the most important parameters, and the nitrogen content can be as high as 12% in particular resins, and water content can be as high as 15%. By casting high quality steel, we tend to use the highest grade furan resin, which has very low nitrogen or water content, or even zero. There are solutions on the market. For iron castings, we use medium or low nitrogen and water content resins. And the very limited application of furan sand in light metal casting is confined to the low-grade resins. When it comes to technological properties, we can achieve high dimensional accuracy of the part with furan sand. Molds and cores made of furan sand has high strength and excellent shakeout properties, and the mixture is quite good. It has quite good reclaimability. On the other hand, it's quite temperature sensitive, so we have to control the temperature during molding and mixing. And the residual nitrogen and sulfur level can cause us problems when it comes to formation of particular casting defects. Next, please. The polyurethane cold box, or just simply cold box system, is a gas-cured cold process, which means that the bonding will take place through chemical reactions, which is triggered by gas curing, and it happens at room temperature. The main component in this system is a phenol-based resin, which is produced by different condensation reactions of phenol, cresol, or formaldehyde. In PUCB, we have activator, which is in most cases a polymeric isocyanate, and we have a liquid, we have a vapor catalyst, which is triethylamine or diethylamine vapor. And the curing mechanism is quite simple, but a bit more complicated compared to furan sand. We have two liquid components mixed to the sand, and then we have to pass amine vapor through the geometry to have a solid mixture, to have a solid urethane structure at the end. Next, please. The cold box system is mainly used for core making due to the gas curing, and the core making happens at high production volumes. Commonly used parameters in ferrous applications is 1 to 2% of resin, in which we have 50 by 50 distribution of phenol and isocyanate based on the weight of the sand. And then we pass through amine vapor through the sand, approximately 0.4 to 0.6 cubic centimeter, counted on 1 kilograms of mixture. The cold box system has quite good shakeout properties. Surface finish is quite good for castings, but on the other side, as a technological difficulty, we have to have a gas generator in the system, which is necessary to convert the liquid amine into vapor. The cold box mixture has a tendency to waning in the castings, but this can be made up by different additives. Regarding patterns, we can use any type wood, metal, or plastic patterns for this system. It doesn't really matter. But we need to have a chemical scrubber in the system also, which is necessary to neutralize the exhaust amine gas, which is not used directly in the curing. When it comes to coatings, we can use basically all types of coatings for cold box system. Next, please. The epoxy sulfur dioxide process is one of the most complicated chemically bonded system solution. It is a gas cured process, which means that the bonding will take place through chemical reactions due to gas curing, but sometimes in order to speed up things, we need to have elevated temperatures when it comes to the sand geometry and the core or the mold. Its main components are epoxy resin, or sometimes you can use furan for this purpose. We add epoxy resin in 0.6 to 1.2% level based on the weight of the sand. We have an oxidizing agent, which is in most cases peroxide, approximately 0.2, 0.3%. And we have a catalyst, which will speed up the reaction, which is sulfur dioxide gas. And the addition of this gas is depending on the peroxide content we have. This mixture is basically used for coal making. Next, please. If you take a look at the curing mechanism, it's a bit different when we compare curing furan resin with the sulfur dioxide and epoxy resin. The main difference is that during curing of furan resin, we have heat as byproduct during the polymerization. Next, please. When it comes to technological properties, epoxy system has quite good properties when it comes to nitrogen levels. So it is quite popular for gray iron and ductile iron castings, because there we would like to avoid nitrogen, of course. This mixture has unusually long bench life of the mixed sand, so we can mix the liquid components together, and then without curing we can store them for weeks, basically, which is quite advantageous. It is suitable to use any type of pattern when it comes to the epoxy sulfur dioxide system. But on the economic side, a wet scrubber is again necessary to neutralize the gas we don't use particularly for the curing. And this has to be done by some addition of units. When it comes to coatings, we can use any type of coatings to this mixture. Next, please. The water glass carbon dioxide system is a gas-cured cold process, which means that the bonding will take place through chemical reaction, which is triggered by gas curing at room temperature. The main component is a liquid water glass, which is generally consists of silicon dioxide, sodium oxide, and water. And the main parameters in a liquid water glass is the silicon dioxide sodium oxide modules. These modules will decide what kind of applications we can go with when it comes to using liquid water glass. In first application, we usually add 2 to 6% binder based on the weight of the sand. And the gas curing will happen with the carbon dioxide. The curing mechanism is a multiple stage process. In the first phase, we can achieve an initial strength, which will develop during the gassing with carbon dioxide itself. Then after 24 hours in phase 2, the natural dehydration of the mixtures will double the initial strength we can achieve during gassing. And this process is mainly used for core making. Next, please. One of the main disadvantage of using a water glass system is the bad shakeout properties, and it has exactly something to do with the residual compressive strength of water glass. And this graph, you can see the residual compressive strength versus the curing temperature. And it is quite obvious that in the temperature range of casting iron, so around 1200, 1300, the water glass system will have the highest compressive strength. That will make the shakeout quite difficult when it comes to curing iron. Other than that, the technological properties, we can use any type of sand for this purpose, silica, zircon, chromite, or olivine. But the sand temperature should be ideal between 18 to 23 Celsius. When it comes to this bad shakeout property, we can make it up with different additives, for example, sugar or coal or iron oxide. And then we have a quite acceptable shakeout properties using the right combination of additives. We can use any type of pattern, wood, metal, plastic for this purpose, but the water glass system is very sensitive to humidity. So when it comes to coatings, the alcohol-based coatings are recommended. Water-based we cannot use directly for the water glass system. Maybe if we can solve the immediate drying of the coating, it can be a thing in the production. Next one. So as a summary, I would like to say that the choice of the right molding material will always come down to the geometry of the mold and core you are planning, and of course the production volume, so how many we need. But at the same time, we also have to consider a lot of economical and environmental things at the same time. So it's a quite complicated question to pick the right molding material. We hope that we give you some hint what you can choose from. And I would like to emphasize some further reading if you are interested. We have a chapter, Molding and Casting Processes, in the ASM Handbook, Volume 1, on cast iron science and technology. So there we have a quite broad description of all these things we just talked about. Yes, next one, please. And here we will take a look at the clip, an interview I made with a foundry expert lately, and he will talk about more practical things when it comes to molding materials and sands. Thank you.
The most exciting questions about molding materials which can pop up in a foundry are, for example, how to choose the best sand system for the manufacturing, what types of machines are needed for the production of molds and cores, and what are the biggest challenges and future trends in the topic of molding materials. We are now going to find the answers together with Sten Bergman, sand expert from Volvo Foundry. Welcome, Sten.
Thank you.
So, what are the most important aspects in a foundry to choose the appropriate chemically bonded system?
Expecting that it must fulfill all the qualities for making good cores and such things. I think environmental is the biggest issue. Yeah. And especially for the outside and also the working environment. And I'm thinking especially to avoid chemicals that are on the REACH list, yes, or as for us on the Volvo Grey and Black list. Okay. So it can take that a lot of chemical systems are not able to use.
All right. And the application of epoxy sulfur dioxide system is very rare in the world. What is the idea behind that you use it in Volvo Foundry?
It's quite long history, must take in 30 seconds. Okay. So it started in the early 90s, yep, we had to choose a new core making method. And the first choice to make a cooled method was the first choice. And when it was standing behind the common cooled bauxamine and with epoxy as a two system.
Okay.
And in the end, that comes over to the epoxy system. What was the resin was solvent free.
All right.
Was one environment reason. And on the technical side, it was that it has very short cycle time.
Yes.
And also very long bench life.
All right. And what is the machinery background and material demand of a chemically bonded sand line, for example, in Volvo Foundry or in general?
Both in general and especially for the Volvo Foundry, we have the first is naturally the sand handling.
Okay.
And the first most important thing is to keep the sand tempered and dust free.
Okay.
And we do it in Volvo by having a sand heater and dust removal just before the mixer.
All right. And it is right after the silo, or where is it located?
It's located just over the mixer in the foundry.
Okay. And what is the machinery background and the material demand of a green sand line in the Volvo or in foundry in general?
Of course, in a green line system, the sand preparation is very big issue
Okay.
overall. And you need to prepare the sand that comes back,
Yeah.
first by moisturing it back and cool it down.
Okay.
Sometimes you can do it in the same machine or in separate
All right.
machines. And when you need a good mixer and a system that can add the additives you need, the coal dust and the bentonite,
Okay.
or a third part or whatever.
Yes.
And when actually a very good molding machine.
Okay.
And when it's a lot of transport system from through the line and core setting and all these things that are needed.
Yes. Okay. And what are the most important factors in controlling and maintaining a green sand line in a foundry?
For just the properties of a green sand, the common is to have a control of active clay
Yes.
and the carbon content, and actually the compactability is free that you use daily.
Okay.
And when of course it's important to have a good control what's coming into the line from the core making to keep it constant, all these figures, as constant as possible.
Okay. So constant is the key word.
Yeah.
Okay.
And also one thing that you perhaps forget is the mechanical maintains,
Okay.
especially on mixers and molding machines and all things that are wearing out.
Yes. Okay. And what are the governing aspects in handling sand, particularly in a foundry?
As we mentioned in the core shop, so easy to keep the sand tempered, especially with all modern system. I need a temperature between 20 to 25 or
All right.
20 to 30. So in the best ways you should have the tempered sand, both
Yes.
cooling and heating, and at least heating here in Sweden.
Yes.
And also important to have with dust removal, as we said earlier.
Okay.
Dust is always a disaster for making cores.
Okay. And what about the storing such additives like bentonite and coal dust?
Much more easier.
Yes.
But for a bentonite is to have it working is to avoid all contact with water,
Okay.
both directly water and all condense,
All right.
when it will stop to be able to blow and handle.
Yes.
And for the coal dust, it can be to have a control so it's not self-ignition.
Okay. Yes.
But you can control to have a temperature control in the silo.
All right. And it is very hard to store coal dust?
Normally you buy a product that is diluted with bentonite and when you
Alright.
avoid this problem.
All right. Okay. And what are the governing aspects behind storing and neutralizing binders and resins, such chemicals?
Of course, depending on what system you have chosen,
Yes.
what chemical you use, but at least you must fulfill all laws that
Yes.
are on the system. That is a lot.
All right.
And naturally to have a very safe handling and safe storage.
Yes. And how does it work in, for example, in your system with the epoxy SO2?
The epoxy system has two chemicals that are critical, you
Okay.
can say. The sulfur dioxide,
Yes.
that is a poison gas under pressure.
Okay.
So it means we have a lot of systems to secure that it can leak out.
Okay.
And we also use with organic peroxide
Yes.
that has a lot of laws around it.
All right.
So it means, for example, it has a special building for the storage that is more or less built so it can burn in it and without making any accidents.
Yes. And does this demand worth to use epoxy SO2 system?
Yes, we think so.
Okay.
For us it is. It must be big series and
Okay.
serial production.
Yes. And because of the high production rate you can
Yeah.
make with the system.
Yeah.
All right. And most foundries used coatings, but why is coatings important?
I would say that some castings would not be able to produce
course.
without coatings.
Yeah.
And especially if you come to these complicated castings, that's cylinder heads
Yes.
or hydraulic goods,
Okay.
when it wouldn't be clean inside without coatings.
Okay.
Or you have to use much more expensive sands or something like that to solve the problem.
Yeah. And it also helps to avoid casting defects.
Yeah, it's always a cost in the end.
Yes.
How to get a clean casting and at the lowest cost.
Yeah. It is the most important factor,
Yeah.
of course.
And it means also if you have an easier casting, it may be possible to use it without coatings
Okay.
or just coating special parts of the core.
Okay. And what happens with the molds and the cores after the casting is solidified and after the shakeout?
Oh, if you take it as in a green sand
Yeah.
system you're thinking about.
Yes, for example.
Yeah. When the cores are normally, if it's chemical bonded system, they
Yeah.
are collapsed, so binder has burned up more or less.
Yes.
So it means that the sand falls together into the old green system, green
Okay.
sand, and together it will go back to the sand
Yes.
preparation. So it means that the core sand will be, the next step it will be the green sand.
All right.
Mm.
Okay.
To just add the bentonite and coal dust that you have lost.
Yes. Yeah. During the production.
Yeah.
Okay. And what do you think as a foundryman? What are the most important challenges the molders and the core makers facing in the future?
Oh, it's a lot of challenges.
Okay.
But one is, I think, what we have seen during the years I've been working with, that the demands on the casting will always increase.
Okay.
We will make castings with thinner walls.
Yes.
That means that you can't accept any enclosures anymore,
Of course.
or you need even better cleaners inside, depending on smaller, better cooling. Yeah, it must be more perfect.
Yes. And environmental laws are become more strict and strict.
Yes,
Yes.
they will be more and more tricky, as we mentioned in the beginning, that we perhaps some chemicals are not allowed to use anymore.
Yes.
When you must find new solutions.
Okay.
And you also have ways that you shall make the production carbon dioxide free.
Okay.
Is
Yeah.
one big challenge.
Yes.
And yeah, the whole environment side is a big challenge.
Okay. And how do you see what trends are coming in the mold and core making area?
The trends, you can see that the old hot methods
Okay.
are more or less
so
going
the
out.
thermosetting method.
Yes, thermosetting.
Okay.
It will be, I think, cooled methods
Okay.
and mainly gas cured
Yes.
or just air cured. But I think it will go that way, and hopefully it can be something that is more environmental friendly also.
Yes, and it is because the thermosetting processes has more environmental load and chemicals.
No, but it's more for working environment.
Okay.
We heat together and such
Yes.
things.
Okay. And what do you think? Can the new type of inorganic systems cured with hot air can break into the cast iron manufacturing process, just like they did in the aluminium casting of cylinder heads, for example, recently?
As it looks today, I think it must come something new, not based on water glass,
Water glass, okay.
because it has physical or chemical
Yes.
aspects that is very difficult to give with high temperature.
Yes.
That is sinter the sand, and
Yes.
especially if you have out the sand after.
Okay.
Because you're talking better cleanness, I think this is very hard challenge to do at the same time with
Yes.
water glass.
Yes, and the shakeout will be also
Yeah.
worse. Okay.
for example. But for a working environment, it should be very good.
Okay.
But hopefully it comes something new that can both make it technical and environmental
Yes,
at the same time.
Exactly. Okay. Thank you very much for the interview.
You're welcome.